Example 6 is a question from the sample exam from 2015, and it gives us a piecewise function. We have two semicircles and two straight lines, and it looks like it's discontinuous at 0 and has a kink at 1. Okay, although it's discontinuous at 0, there is a point defined at 0. Okay, it's 0, 2. Now, it tells us that the graph has a vertical tangent at -2, so I've drawn that in blue. There's a vertical tangent line there. And there's horizontal tangents at -3 and -1, which is also drawn in there. And question asks, what are all the values of x on the open interval at which f is continuous but not differentiable? Okay, so it is continuous at all the way to 0, and it's not differentiable at 0. Now, it wants both continuous, so I'm just going to highlight that. It wants both continuous and not differentiable. So there's two conditions it needs to meet. And at 0, it's not continuous. It's not differentiable, but it is continuous. So it fails the first criteria. So at x equals 0, we can kind of eliminate that because although it's not differentiable, it's not continuous. Where it is continuous but not differentiable is going to be at the kink. Okay, so it's going to be at x equals 1 and also at x equals -2, because although it's continuous, it has a vertical tangent, which means that the derivative is not defined there. So at x equals -2 and x equals 1 are the 2 points where they both are continuous and they both do not have a defined derivative. Okay, the blue one is because it's a vertical tangent. The green point is because it's a kink. For part B, so the answer is going to be, in this case, oops, I forgot to answer this question. So this is a multiple choice question. So the answer is going to be C. Okay, so part B, g prime is equal to f of x. So the f function given is now a derivative of some antiderivative function g. It says, for what values of x on the interval is g continuous but not differentiable? Okay, so if we have a continuous derivative, that means the function was smooth and continuous and differentiable. Okay, so as long as it's continuous, the antiderivative was smooth and continuous. Now in this case, we have continuity all the way through except for x equals 0. Okay, so that means then the derivative does not exist because it's not the function does not exist, or sorry, the function is not differentiable at that point. Okay, that's continuous for all the other points, so it must be differentiable. It is not differentiable at that point, and it is continuous for all this point. And the reason why it's continuous, I'm just going to highlight that. Okay, the reason why g of x is continuous because the domain is defined for the whole interval. So the domain of f, I'm going to just maybe make this more clear. So the domain of f is all real numbers. Okay, therefore, g is continuous. Okay, so that's why we have continuous. Now, where it's not differentiable is where the f is discontinuous. So g is not differentiable. Okay, so g is not differentiable at x equals 0 because it's discontinuous. F is discontinuous. G prime of x, which is f, is discontinuous. Okay, so it's continuous for all values, but it's not differentiable because of that discontinuity on the derivative at 0. Part C says f prime of x is equal to h of x. So h of x is the antiderivative of h. Okay, sorry, the h is the derivative function of f. So I want to look at this f graph and I want to differentiate this. So I want to know what the derivatives are of the different points. So for what values of x on the interval is h discontinuous? Okay, so when we take a look at the slope, we want to have smooth and continuous, means that the graph of the derivative of f, which is h, as long as f is smooth and continuous, we have derivatives. Okay, so there's a problem in a couple points. Okay, one of them is when the derivative is infinite. So when x is equal to -2, f prime is infinite. Okay, it's a vertical tangent, so the graph is discontinuous because on one side it's going to be, we're going to have an asymptote there. So we're going to have a discontinuity based on the asymptote. The derivative doesn't exist at endpoints. So at x equals 0, and maybe I'll write through this in, so we have a 0 coordinate here. At x equals 0, it's discontinuous. Okay, so it's the the derivative is discontinuous, so the function is discontinuous, so the derivative is discontinuous. So that is another point of discontinuity on the derivative. And the third point is going to be where there's a kink. Okay, on one side it's going to be positive, the other side negative. So the h, or the derivative of the f graph, now jumps from a positive to a negative. So at x equals 1, again, the derivative of f, which is h, will have a discontinuity. Okay, so we have 3 points at -2, 0, and +1. We have the derivative of f being discontinuous. In example 7, it says, which of the following functions show that the statement, if a function is continuous at x equals 0, then it is differentiable at x equals 0, is false. Okay, so if there's continuity but a kink, that's when we're going to have a non-differentiable point. So that would make this statement false. So which functions will have this kink at x equals 0? Okay, well, one of the things that we could do is we could differentiate these to work this out. So we could do that. We can analyze the graphs as well. So in this case here, so for A, this is f of x is equal to x to the power -4/3. There's already a vertical asymptote here, so we know that this is discontinuous at that point. Okay, so it fails the first test. So we can say that that is false because it's discontinuous. Same with b. b is already in the denominator, so it already has a vertical asymptote. So again, it doesn't pass the continuity test. When we take a look at D and E, these derivatives will not generate a non-differentiable point at 0 because we can evaluate their derivatives at 0. So we can just kind of eliminate those. And E is just a cubic function. C is going to be our answer because when we differentiate this, well, first of all, this is a cubic function and it's going to give us a vertical tangent at x equals 0. Okay, so we're going to have a function that looks like this. Okay, and when we differentiate this as well, you can see that the derivative is going to generate a denominator, and a denominator being equal to 0, well, that can't happen, so there's a vertical tangent that's going to fall through that point. Now, I didn't draw that very well, but this is going to have a vertical tangent through that point because it's going to slide through that point like that. So the answer is C. The second part of this question says, is the opposite statement true or false? Okay, the opposite statement will be that if it is differentiable at x equals 0, then a function is continuous. So, that's going to always be true. Okay, because if a function is differentiable, that means the function is smooth and continuous. So then it must be continuous at that point. So that's opposite statement will always be true. So I'm just going to save that. Opposite is always true. Okay, because if differentiable, then must be continuous.